Someone asked about blood pressure and what it adds to analyses. I'm not going to talk about that specifically here, but I'll try and remember to point it out. Blood pressure is tied to respiratory rate, which is tied to heart rate. Those are all collinear. And so I think at this point we don't know what the individual contributions of each of those things are, but you will certainly find effects in any of those if you're looking for them, but they may be collinear with other effects. Another question is about head molds, specifically the case forge ones. I have experience with those. I mean, it makes sense. It does improve the data some. It's not a magic bullet. There are a lot of subject-specific issues that come up, often to do with hair or to discomfort, like with discomfort on the face, things like that. And someone asked about censoring. Usually it's okay, unless you're presuming something about the contiguity of time points. But most analyses will permit that. Okay, so we've got it up. My name's Jonathan. If you want to get in touch with me, there's an email there, or you can just Google me. I have a website, and if you like what you see here, a lot of the stuff here is on that website, and you can just download it, scripts, demos, things like that. So I'm not going to talk about particular artifacts or particular denoising methods, although I will illustrate artifact and denoising methods. What I'm more going to try to do with this 25 minutes is illustrate an approach to looking at data, and it's going to be purely single subject approaches today. It's not about group level statistics or trying to prove things statistically. It's letting your eye do the stats for you for the most part. And I'll just say that both Steve and Alex, who's my postdoc advisor, gave me a lot of leeway, created a lot of time for me to delve into the parts of these things that I thought mattered. So I'm grateful to them for that. I'll show you data from a lot of sources today. One data set's from Prantic. It's a multi-echo data set. So most of these data sets are anywhere from like 50 to 200 people. In this case, there's 4 echoes in this multi-echo data set. The other data sets are all single echo. The data were acquired anywhere from like 1 to 2 years ago to 15 years ago, so it spans a large range of data qualities, including multi-echo data, multi-band data, kind of legacy data, the Abide data set, things like that. And here are the other kinds of data that I'll show you. So I'll show you data from the NIH, from Alex's lab, stuff I collected at WashU or that other people collected for me at WashU, some stuff from the Abide data set, from the Randy Buckner's Genomic Superstruct Project data set, and then the Connectome project and Russell Boldrak's MyConnectome data set. Those latter two are both kind of fast TR data sets. So I think Javier had in his talk in bold, look at the data. So when I started my postdoc, I kind of approached processing from scratch, tried to make it better, faster, more modular. And after a few months, I kind of arrived at something I was really happy with, where I could process any data set from scratch with about 5 minutes of intervention on my part. And at the other side would come out movies like what you just saw there. And what you were looking at is the free surface segmentation of a handful of subjects from Randy's data set. And I think it's really important to look at the data like this. And you also saw the masks being eroded. So you saw the green mask of the white matter being eroded down over time. Can I go backwards and forwards on this? Oh, there we go, left and right click. So you see the masks being eroded. This is going to come up later on. And I'm doing that both for the CSF and the white matter masks. All right? But it's important to lay eyes on these masks because although FreeSurfer does a pretty good job now, 10 years ago that was not really the case and you needed a lot of user intervention. Making movies like this is easy and it serves a variety of functions. It can show you how well your segmentations are working. It can also show you image alignment across scans. So this is Russ Poldrak's data, and I'm just showing you, I don't know, a dozen or 2 dozen scans. And you can see that the data are just really well aligned. You can't even see evidence of anything moving in this case. So it's nice to have numbers, but when I want to assess segmentation or alignment, I want to see it. And I think it's been really useful for me, at least, to automate this and to turn these into movies so that you can actually lay eyes on it like we all say we ought to without having to click around and push buttons and sort through folders and crap like that. So if you think that things like this are useful, there are demo scripts up at the website where you can hopefully adapt them pretty quickly to your own processing pipeline. And the point I want to drive home with this is that it's possible to do high throughput, close scrutiny of your data, both structurally and in time. And that's what I'm going to try and drive home for the rest of this talk. And I'll just say, you can read those points right there. I touched on most of those, but I'll say with respect to point number 4 that I have entirely discarded some public data sets that are used in a lot of papers because it's clear that the acquisition did not cover the brain, that parts of the cortex were routinely missed in sites. But if you don't open the data and look at it, you'd never know. So you've seen movies like this. This is just a single subject scan sped up a bit. And with your eye, if you watch it, you can see the head move. So what your eye does, we can also do algorithmically, usually with rigid body transforms, just pitch, roll, and yaw, and XYZ. And I thought I'd just show you a little bit of data about that and about ways to think about the qualities of your data. And these will be in terms of traces. So here I've just got the 6 rigid body transform parameters, XYZ, and pitch, roll, and yaw. And here I've condensed them into something that I call frame-wise displacement, so that the top plot is head position, and the first derivative is going to give you motion, and that's what that red trace is. So there'll be red traces throughout the rest of this talk. That's almost always frame-wise displacement, and I'm pretty much always keeping the scale identical, so you don't have to worry about the numbers too much. You just look at the form of it. All right, so clearly in the scan there are 3 major head motions. You can calculate other things that are not explicitly based on motion estimation. For example, DVARS, I think, is fairly widely used at this point, and it's a very simple measure. You just differentiate, just like I differentiated position to get motion, you differentiate a bold image with respect to time by backwards differences or whatever, and then take the mean value or the RMS value at each time point within the brain. And so the way to interpret something like this, is there a cursor anywhere? Not really. Pointer?
With the mouse. There should be.
Is it? I don't see it. Well, at any rate, you can imagine a pointer that's pointing at things here. There's some baseline level of signal change on average throughout the brain. A lot of that's due to white noise or thermal noise. But when you have punctate changes in the DVARS signal, that's almost always due to motion. And it's easy to think about it because you have, let's say, a very low signal outside the brain, then the brain moves into it and you get high signal for a little bit and maybe it goes back down. Or maybe the brain stays there, but now it's not changing signal anymore. And so you get huge changes in signal when the brain moves, vacating portions of the imaging box and filling other portions. Another, I think, maybe less recognized way to come up with a data quality trace is to run something like AFNI's 3D D-spike. Now this isn't a summary. What this does is it looks at every single voxel signal and just looks at some local window of it and says, so here's what my typical signals is. Do I have any outliers? And if so, where are they? And I'll just kind of interpolate that, get rid of those outlying spikes. As you can see, during times of motion in this image, about half of the brain is replaced by 3D D-spike. And it's clearly happening at the same times of motion. And this isn't cherry-picked, this is just how things typically are. Okay, so there's a lot of ways to get a sense of when you're having problems in your data, when the data are unusual or abnormal, and when you're probably going to have difficulty fixing the data. Just as an aside, I want to show you how dependable your estimates of motion are. So this is a multi-echo data set courtesy of Prantic. Up at the top, I'm showing you motion estimates from 4 different echoes. You can't see that there's a difference because all the traces are on top of each other. In the second plot, I show you if your reference volume, so if you have 500 volumes, you have to designate something as your reference, and each volume is individually registered back to that target volume, that reference volume. A lot of people use the first image in a run, or maybe a mean image or the middle image. It doesn't matter what you use. You get the same answer every time. It doesn't matter what interpolation technique you specify. It hardly matters any of the settings that you apply during motion estimation. Even it doesn't really matter that much what software package you have. Down at the bottom, AFNI, FSL, the WashU 40FP tools are used. I think I put SBM in there too, yeah. I mean, there's a little bit of difference, but not really much worth talking about. But I'll tell you 2 things that really do matter, and I'll unpack it a little bit too. First, if you de-spike the data first, you produce very large changes. So hopefully you can see that there are large red peaks and then half-size gray or under half-size gray peaks with de-spiking and then slice time correction. And it doesn't matter what you do first. slice time correction or despiking, both of those produce dramatic decreases in the motion that is estimated in an image, and also the motion that truly is in that image. So let me show this to you. A different multi-echo subject, you can see at top the 3D despike trace showing you that lots of the image is being replaced during times of motion. In the middle, I just chose 3 random voxels. The original trace is in black, and then the orange trace shows what 3D despike's output is. And so you can see that there's a few, you have jagged black parts showing original data, and then that's been smoothed over more or less with the orange time series, which is the post-despiking data. So I'm going to unpack 5 volumes circled by those ovals that just came on the screen. All right, so at top is the original data. And you can see the beginning and the end look okay, but volumes 212 and 213 have this striped appearance. And actually the front of the brain is serrated like a knife. That's what the data actually are like. But when you apply a despiking routine, it looks at that serrated part that's jutting out of the brain where it didn't used to be and says, well, that's pretty unusual. I'll take stuff from the time before and stuff from the time after and put it there instead. And then the brain looks a lot more normal, but that's just because it's built of brains coming before and after, right? It's not the real brain anymore. Here's a different subject. A big motion, dramatically decreased by despiking. I'll show you this little segment of time here. So at the top again is the real data, the raw data. The bottom row is the despiked data. And at a glance, you can see that there's, that striped banding pattern in volume 64 and 65 and 66, and that's attenuated or gone. In the volumes below it, and you might think, well, that looks better. I don't know if you can see this well. I've put reference markers to show you where the brain is, and you should be able to see, hopefully, that in volume 64 and 65 in the original data, the head tilts backwards, right? The front of the head lifts up and vacates that oval. But in the lower row, the despiked version, the brain is back where it had vacated space. So the point I'm trying to make is that from first principles, we should know that temporal interpolation is going to decrease motion in a scan. And it does so pretty dramatically, okay? So I think it would be useful if you consider estimating motion in the raw data, unprocessed data, because that's going to give you, unavoidably, once you temporally interpolate it, there's going to be less motion, and it's going to be less useful for you in the sense of detecting abnormalities in the scans. Another point that I think comes out of this is that despiking occurs mainly at times of motion, and you ought to think of it as statistically related to censoring. So it's not like you do one or the other. It's a spectrum here. All right. So at this point, I'm going to bring together the 2 parts I've talked about so far, the traces and the segmentation, to start talking about the temporal qualities of the bold data. So this is Russ Boldrak's data. So it's a multi-band data. The voxels are about 2 millimeters, I think. The TR is something like 700 milliseconds. 2 scans at the top. You can see that, first of all, there's a low-level amount of motion wiggling. That's respiratory motion that you can see because it's no longer aliased at these faster TRs. And then there's a few spikes of larger head movements. At the bottom, I'm showing you Russ's brain segmented. And then I'm using dark green to show you the deepest white matter that's furthest away from gray matter. And then the lighter shades of green at the bottom are white matter voxels that are closer to gray matter. When I take these scans and turn them into the gray plots, for example, on the left column, there's a green line, and above that green line is all gray matter. Below that green line is all white matter. And they're ordered by compartments. I think maybe the bars are too small to see well, but there's a light green, a middle green, and a dark green at the bottom. And so I'm ordering it proximal, medium, and distant from gray matter. And this will become relevant in the next few slides. So in this image, which I think is from the special issue article, what I'm trying to show you is the effect of thermal noise in your data. And I'll just show you a couple of Russ's scans. So this shows you, you don't have to look very carefully at this. It's just kind of a gestalt that you're trying to get. But you can see that there are motion-related signal changes that pervade the gray and the white matter. And you can also see that a lot of things snap out when you spatially blur the data. I'll play that just one more time. So the first image is the raw data, and the second image has a Gaussian smoothing kernel placed over it. And you can see a lot of signals kind of popping out from the noise. And all this is a visualization of the thermal noise that you know is there. All right, this is noise that gets in the way of your modeling, gets in the way of your regressions, gets in the way of you seeing the signals underneath it. All right? Right. So I'll just show you, to give you a sense, some people from the Utah site of the Abide database. And this just gives you, these scans are entirely typical. I've looked at thousands of subjects at this point. This stuff is representative. There's not sites that are particularly good or particularly bad. In general, everybody gets about the same bang for their buck in terms of data quality. And then here's some stuff from the NYU site. And this is about, I think, 6 minutes of data. The Utah site had about 10 minutes of data. Russ's scans were a bit longer. But you can see all this, you can see, first of all, that there are a lot of signals in this. There's a lot of global modulation of the signal, which is what a vertical band would look like. You can also see it's present in the white matter. By definition, we tend to consider signals that are present in the white matter artifact, but I also want to point out that they fade with depth in the white matter. And so you might think, well, this is partial voluming, and that's certainly true to some extent, but this happens to similar, like quantitatively it happens in a similar way in the Human Connectome Project data and Russ's data and in all the high resolution data that I've looked at. So I don't think it's just partial voluming in older data sets that we're looking at. So I've looked at a lot of scans in this way at the single subject level, trying to understand what is causing signals and which ones I like and which ones I don't like. And I'll just organize kind of schematically things for you. This is how I think of it, at least, at kind of the highest level. So at the top, so there's each column is a site. So I've got the NIH, an Abide data set, Randy's data set, and Russ's data set. And I've got 4 scans ordered vertically from each of these. At the top, you see people who just don't move. And you have hardly, they have pretty modest global fluctuations in their signal, which would manifest as big black and big white vertical stripes in the data. Then you have people in that second row who have large modulations of global signals. And it's present in the white matter for the most part, too. In the third row, now the people in the second row are not moving very much. So it's not motion artifact, right? And the people in the third row have the same global modulations of signals, but now they're time locked to motion in many cases, right? You can see that instantly. And I'll skip the bottom row for now. There are a lot of ways that you can unpack those observations, and I tried to do that in a paper recently, but I'll go to one of what I think are the more important features of it, which is to now bring in physiologic records. And I agree very much with Dan that it's very helpful to have physiologic data to help you figure out what it is that you're seeing. So in blue is the respiratory belt waveform. So it's just an elastic band around someone's waist. That's all it is. And in green is heart rate estimated from a pulse oximeter. In gray, related to someone's question earlier, is the peak amplitude of the pulse ox, of the pulse ox trace. And then in black is the global signal. So for example, in the upper right, you see some big vertical black bands, and you can see corresponding dips in the global signal. The thing that I wish I had a pointer to point to you was, if you look in that middle upper panel, you see there's a high spike in the blue trace, and then it dips down for a little bit, and there's a black vertical band right underneath it. That's a person breathing in deeply and then not breathing for a while. And you see that there's a big black stripe right below it for about the next 30 to 40 seconds. That happens also in the right upper and in the left lower panels. So what this strongly indicates is that these huge modulations of bold signal throughout the brain are respiratory artifacts. And I'll call it noise. I mean, it's a bold signal, but it's not bold signal that I'm particularly interested in because it's a product of ventilation. Okay? And you can see the bottom middle panel is pretty interesting because I think actually both of these bottom panels are interesting because they exhibit the large amount of variability that you can have in people's breathing patterns. So if that bottom middle one, you see almost like square waves in the respiratory pattern. The person didn't breathe for 2 minutes, hardly, just very shallow breathing. And then they breathe really deeply for 2 minutes. And you see huge changes in the bold signal that correspond to those things. But you wouldn't know this if you didn't have respiratory traces to go along with it. So that's why it's really helpful to have, in my view. So I'll just close out the talk by showing you a few things related to denoising. I think Javier said it earlier, it's very important to know where you start and where you end up, okay? And so I'm going to try and show you both of those things right now. So at the top are 3 of the scans from the previous slide, and I'm just putting, I think there's just the respiratory trace and the motion trace up at top. And then the same gray plot that you saw before, the data as it is, without any attempt to try and get rid of problematic signals. Now you've heard about recording cardiac traces and recording respiratory traces and transforming them with RVT or using the respiratory response functions. If you use such approaches, that is the second row. Okay, this is supposed to try and take care of respiratory variance. And I think it's pretty apparent that there are still big vertical black bands when people breathe. They are attenuated sometimes, but it's nowhere near accounting for the variance that we think ought to be accounted for by respiration. A lot of people regress motion parameters or white matter signals or CSF signals. That's the third row. And you can just see from these plots that as you get further and further away from the gray matter, that things like respiratory signals are just not carried by the deep white matter. So it's not helpful in that regard. You can toss all these together. That would be the fourth column. You can add the global signal in, which explicitly takes away shared fluctuations across the brain. And of course, that gets rid of those. But you can still see that at times of motion, for example, about a third of the way through the first scan, you can just see there's kind of a vertical salt and peppering. That's due to motion artifact. That's not taken out. So no single denoising procedure rids you of all the artifacts. They each have different properties that they're able to tap into and take care of. And there's not like a one-stop shop for this stuff. So those are some of the model-based versions. You can do data-driven approaches too. I see as by far the most popular version of doing this. I'll just show you Human Connectome Project pre and post fix, which is the ICA procedure developed for the Connectome Project and recommended for it. And this also is useful because it illustrates the variability and the quality of the traces. So the motion trace is really ratty, right, relative to the ones that you saw before. It's not clean. This is more or less true of most of the Connectome Project data. Also, the respiratory trace is kind of crappy. Now, that's true of a lot of physiologic data, like Dan mentioned. A lot of people only look at it post hoc, or maybe it's collected by an RA who doesn't know what the person analyzing the data is really going to be looking for. But those blue traces earlier are really useful traces on the NIH data. These traces are not so great, but what you can see is that where these big black bands exist, there are pauses in the respiratory trace right before it. There's a big slowing in the respiratory trace. So these, again, are yawns, like people bored in the scanner with these 15-minute connectome scans. So with your eye, you can see pretty clearly what is and is not taken out by ICA. So I'll just close with the last minute or two with some slides on multi-echo data. So this was brought up before, I'll just reiterate it. In an ideal world, we would excite a voxel and then wait 30 or 40 milliseconds, collect at the TE, and then we get that red point right there. So this is 6 TRs worth, 6 volumes worth of data, and just an ideal single signal. What you get is the red point at your TE. That's single echo data. And when that goes up or down, that's what for the past 25 years we've talked about when we talk about signal going up or down. In reality, it's not quite like that because at time 0, the signal is not the same at every volume. And so our S naught, our starting intensity, is not the same. So when you record a single signal, you don't know if that's because the signal decayed faster or slower, or if you started from a higher or lower intensity to begin with. You just fundamentally can't get around that. You have one measurement and two parameters. So what multi-echo does is, for example, with 4 echoes, like the data that Prantic and I have worked on, you can explicitly model where you start and the speed of the decay rate. Okay? So a multi-echo data set looks like this. Here's 4 echoes. It fades over time. That's just the signal decaying. You can see the CSF remains bright. It decays much more slowly than the white matter. And here's what the signal at that little red voxel looks like. You can see it decays. You can fit it with an exponential curve. There are a variety of ways that you can approach data in a multi-echo way with, but I'll just show you 2. All right, and so you can fit at every voxel on every time point, S0 and T2 star. So if you use MICA, which is a very cool approach to utilizing the multi-echo properties of data, up at top, there's your motion trace in red, the optimally combined data, which you can think of just as a single image summarizing it all, is up at top, and it's decomposed into an S0 trash component and a T2 star bold component. And that's what's on the bottom. But also you can see that there are huge vertical black bands in the bold component, which is sensible because that's a respiration artifact, which is a T2 star phenomena that you fundamentally can't get rid of with multi-echo. And it doesn't matter if you use MICA or if you explicitly fit things with an exponential function, you arrive at the same answer. So there's no single magic strategy for denoising. Everything gets you partially where you want to be, depending on the properties of your denoising technique. All right, so I've shown you nothing at the group level, only single subject data, and this whole talk is an argument for looking with your eyes and for trying to help everybody look at data with their eyes. There's 2 articles at the bottom, one's in the special issue, the other's also out in NeuroImage. And if you start making the simple things, pretty soon you can start making more complicated things. And you can imagine that things like this can become pretty useful for you. So thank you for your attention. I'll take any questions if I have time.
Okay, we have time for 1 or 2 quick questions. Could you go to the microphone, please?
Actually, I'm quite convinced that there is a correlation between briefing and bold signal, but then came my provocative rhetoric question. How do you know that the briefing effect of cause change in bold signal and not vice versa?
How do I know it's a breathing effect and not?
You did not understand. So how do you know that a briefing cause effect in bold signal and not vice versa? It's not a bold that actually reflect a change in the respiration rate or rate variability.
Do you want me to take this?
Yeah, sure. Yeah.
So I think I understand what's being said. There is going to obviously be something neuronal that could be driving your changes in breathing. If you think about holding your breath, you are causing that to happen, and there are also non-conscious changes in that way. However, if you look in that sense, the temporal nature of those relationships are very different. When we look at something like respiration volume per time or the trace of the bellows, what we're really doing is looking at that as a surrogate for the arterial CO2 changes that are being caused by these changes in ventilation. And the CO2 then changes blood flow, which then changes bold. And that temporal evolution means that there is this delay. And so you'll see a very different relationship in these plots between the respiration happening and then the bold effect. If it was the other way around, you would probably assume them to be much more overlapping, that your bold effects are happening almost before or leading up to these respiration changes.
That can also be explained by the hemodynamic delay.
I think we probably should talk a bit more about this, offline, because it gets a little bit off topic.
Yeah, I mean,
here,
there's a
but we
large
certainly
literature
can.
from the 90s on this, looking at carotid Doppler flow, using forced CO2 alterations. Yeah, sure.
This is actually a simple question. Jonathan, your presentation really was emphasizing motion artifacts, looking at motion parameters as a quality assurance. I've noticed a lot of we have this package with a huge number of quality assurance numbers I have no idea what to do with. Are there other things that are really important to look at, do you feel, in assessing the quality of the scans?
Well, I mean, I showed motion and DVARs and a percent despiked, all of which are returning quite similar information.
I think what you're basically looking at is motion. I mean, one way
It's
or the
clear
other, how
that
you're despiking it, how you're not. That's all motion. I'm wondering whether you feel like it's really important to look at signal to noise. Are there other qualities of the scan that you feel are very important, or you think that we need to concentrate on?
Well, sure, there are many important qualities to scan. I mean, TSNR is important, but if you look at, so, for example, what
Dan was showing earlier about that coil malfunction, you can see that pretty easily in normal QA types of approaches. This gives you more than motion. If you have large scanner artifacts, those are also quite apparent.
Oh,
I mean,
they all land up in the motion, that's what if you're
No, they
looking-
don't
if you're
all end
looking
up in
at
motion.
motion parameters, you see
no,
this.
that's not true.
Oh, okay.
They do
Then
not
I'm-
all end up in motion.
Okay. But DVARS is a motion, oh, it's intensity, okay. All right.
That's right,
Right.
yeah.
Okay, question over here.
Is this working?
Uh,
I'm in?
Yeah.
I'll speak louder. Anyway. So 5 years ago or so, Ziad and some others started this long, difficult conversation about global signal regression and how that can inject correlations, can distort some things. Can you just talk about how you feel about, what's the proper ways to avoid those difficulties and still be able to use the global signal?
I mean, that's a big topic. I think, in short, I would say that the key to all of this, I've talked to, I worked at the NIH, I talked to Ziad about this. I think we actually see eye to eye for the most part. The key is the dimensionality of the data, because if you do a simulation with 2 or 3 signals, of course you're going to get trivially and unrealistically massive changes that you don't want. But if you have 20 signals, the changes are minuscule. So I think everybody has an opinion on this issue, but few people have looked into it in terms of simulating it in a realistic way in their own data. So, I don't want to get into that argument. I have no problem personally with global signal regression. I think that this is like a mountain out of a molehill type of situation.
That's why I wanted you to. Good.
Yeah.
Okay, and last question.
That's a very interesting talk. I'm mostly a clinician, and that might be a strange thing in this room, but I want to go back to the first question that was asked and kind of open up a challenge, which is to reserve the concept that perhaps some of the noise is important, that our brains don't work perfectly all the time, and trying to eliminate all the noise might be eliminating some of the things that are important, for example, in patients with panic attacks, where their respirations do change as a result of stress that is frontally probably driving some things in the brainstem and changing functions that regulate respiration and heart rate and so forth.
Well, there's no doubt.
And
oh,
then consequentially have effects on their ability to process cortically. So it becomes a large loop that removing all the noise might not be ideal for.
Well, I'm going to respectfully disagree. I understand the idea that there are collinearities between clinical status, and I'm a clinician myself. In all aspects of neuroimaging and neuroscience, there are collinearities between the design or between the properties under study and aspects of signals that you don't want to have. I don't particularly care about someone's respiration per se. In the example that you're citing, I'd be interested, presumably, in the neural activity that drives that respiration, that reflects the clinical state of that person. So it may be that someone breathes differently or has a higher heart rate. That's certainly true. A lot of our clinical populations are deconditioned, for example. But I don't want to study that, or I don't want to be unable to separate those things from the neural activity that I'm attempting to study.
Okay, it depends on your goals, and at some
Of
point,
course,
at
yes.
some point we may need to.
Yeah,
be able to
you have a good
study
point. Yeah, it does depend on your goals, and so if you have a good reason to look at the noise, well, then you should look at the noise. I think that's fair enough.
Mm-hmm.
We can continue this discussion later. So thanks again, Jonathan. We are going to have a short break, 10 minutes. We're trying back here at 15:15. In the next session, then, we're going to continue with the practical sessions. We have Molly Bright talking about statistical issues with regression. We have Ludo Graffanti talking about ICA, and then we have Prantik Kundu talking about multi-echo, and then we'll have a discussion at the end. Okay, so see you back here in 10 minutes.